Hello everyone, welcome back. My name is Mr. Cobalt, and in this video I'm going to go over how you find the pH of a weak acid solution when you're given the pH of the salt of its conjugate base. So let's get into this. Okay, so in this problem we have a 0.20 molar sodium chlorobenzoate solution. They give you the formula NaC7H4ClO2, and it has a pH of 8.65. Then they ask, calculate the pH of a 0.20 molar chlorobenzoic acid solution. And so here they're giving you the formula for the acid the weak acid. So HC7H4ClO2. So the first thing you want to do, is they gave you the pH of the solution for the salt, so we want to find the Kb of the sodium chlorobenzoate, because once we find that, we can get the Ka value for the chlorobenzoic acid. So let's go ahead and do that first. So the first thing I'm going to do is write out the balanced equation for the salt, the chlorobenzoate in water. So that's going to be the conjugate base of the weak acid, chlorobenzoic acid. So we'll put in A minus for the ion here, since that's in a minus. And typically your weak acids are represented by HA, the H being the acidic hydrogen there. So the conjugate base would be A minus. So since we're going to start with the salt of the conjugate base, we'll just start with the A minus. That'll react with water. So here we have A minus reacting with water, and that's going to be in equilibrium with HA plus the hydroxide ion that's left. Excuse me. So now I can do my ice table. So we'll set up the ice table like so. So ICE. And so they gave us the concentration, which is right over here, 0.20 molar. So that's our starting concentration, 0.20. And this is going to be ignored. So we're going to ignore water, because water as a liquid doesn't show up in the equilibrium constant expression, as we'll see in a moment. And we're starting with 0 amounts here. Now, typically, we would figure out what the change is in terms of x, and then solve for x using the Kb value. But in this case, we don't know the Kb value. That's what we're going to have to find out, but they did give us the pH. And the thing to remember for pH is that is the concentration of H plus at equilibrium. So they are actually giving you the values of your H plus and OH minus. So we have OH minus here, the hydroxide, but we could easily find the hydroxide concentration using the H plus concentration. So let's go ahead and do that. So how do we do that? Well, I know that pH is equal to the negative log of H plus concentration. And so I can take that, right, and set it equal to 8.65. And then I just solve for this part here by taking both of these and putting them as powers of 10, right? So then I have 10 to the negative log. Oh, the first thing I want to do before I do that is divide both sides by -1, so I can get the negative on this side. Not that I can't do that later, but it makes it easier here. So now I can raise both to the power of 10. So this is going to be 10 to the power of log of the H plus concentration. and that's going to be equal to 10 to the negative 8.65. Now, the thing about 10 to the power of log base 10 is that these are going to cancel out and giving you the H plus concentration back. This is very much like square rooting a square. So if I take x squared, right, and then take the square root of it, they cancel each other out and I get x. So it's kind of like that. So now I have the concentration of the hydronium ion, H plus, right? This is OH minus, we'll get to there in a second. And that's going to be equal to 10 to the negative 8.65. And then when I use my calculator to calculate that, I get 2.238. So 2.238 times 10 to the negative 9. Now, this is my H plus concentration. And so now I can find the OH minus concentration by using this equation. I know that the Kw is equal to 1.0 times 10 to the negative 14, and that's going to be equal to Ka times I'm getting ahead of myself. That is equal to the H plus concentration multiplied by the OH minus concentration. Well, I just solved for the H plus concentration here from the pH, so I can plug that in and then solve for the H plus or the hydroxide ion concentration. So then I plug that in, 1.0 times 10 to the negative 14 is equal to 2.238 times 10 to the negative 9 multiplied by the concentration of hydroxide, OH minus. So OH minus. So now I can divide both sides by 2.238 times 10 to the negative 9 and get my concentration of OH minus. So then when I do that, I get a hydroxide ion concentration equal to 4.466 times 10 to the negative, I think it's 6. Yes, 6. Okay. Now I have the OH minus concentration at equilibrium. So this here is equal to X in my table. Now, if usually we would solve for, we would set this up in terms of X, like so, right? So because this is 0, it's going to shift in that direction to make product. So I'm going to lose an X amount here. I'm going to gain an X amount here and here. And then you would write out 0.20 minus X. And then this would be X, and this would be X. And then you would solve for X using the KB. But in this case, since we have to find KB, we have X already here, so we're going to find the KB instead. So let's go ahead and give us some room here, right? So KB, oh, and by the way, I could have found the OH minus concentration in other ways too, because they gave me the pH. I could have used instead the pKw is equal to the pKa multiplied by the pOH, sorry, and multiplied by the pH plus the OH. I think I said multiplied, I meant like added. So the pKw, that's the negative log of the Kw, which we said was 1.0 times 10 to the negative 14. So that's going to be 14. And then you've got, that's equal to pH plus pOH. Well, I know the pH is 8.65, plug that in, solve for the pOH, and then in the same way that I found the H plus concentration of from the pH, undoing the log, I can do the same thing for the pOH, because the pOH is equal to the negative log of the OH minus concentration. So you could have done it that way as well. So I just wanted to clarify that, because there's more than one way to solve a problem. Okay, so Kb is going to be equal to the product concentrations over the reactant concentrations. So here we're going to have the concentration of HA multiplied by the concentration of OH minus over the concentration of A minus. Notice that I'm not putting water in, because water is a liquid and we don't put liquids and solids into our Kb expressions, into our equilibrium constant expressions. And so now this is equal to what we're going to substitute here. We could substitute x in for both of these, and we could substitute this in as well. So if we substitute x in for that, x times x is x squared. And then this is going to be 0.20 minus x. And so what we can do is just plug in this value for x and solve for the Kb, right? So Kb is going to be equal to 4.466 times 10 to the negative 6 squared divided by 0.20 minus x, which is 4.466 times 10 to the negative 6. And then when we solve that, we get 9.976. 9.976 times 10 to the negative 11. Okay, so now we have our Kb. Great. Now we can go ahead and solve for the pH of the 0.20 molar solution of chlorobenzoic acid. Well, how do we do that? Well, we can use the equation that the Kw is equal to the Ka multiplied by the Kb, where Ka and Kb are the equilibrium constants for the acid and its conjugate base, right? So here we just solved for the Kb for the base here, and so now we need to find the pH using the acid. So we use the conjugate base, so we got that. We got the Kb here. We know Kw. Kw is 1 times 10 to the negative 14. So we're going to plug that in. So 1.0 times 10 to the negative 14 is equal to Ka multiplied by Kb, which we just solved over here, 9.976 times 10 to the negative 11. Divide both sides by 9.976 times 10 to the negative 11, and we get our Ka. And so we get Ka is equal to 1.002. 1.002 times 10 to the negative 14. Oh no, 4. Negative 4. So there's our Ka value. So now we can go ahead and do the equilibrium reaction involving the weak acid and water. So let's go ahead and change our equation. So now we're going to use the weak acid, and again we're going to use the generic formula, which is HA for weak acids. We're not going to write out the whole formula. So here, instead of A minus, we're going to have HA, and then here, so HA is going to react with water to form your hydronium ion, plus whatever's left over is going to be your A minus, the conjugate base. And so again, we're given the concentration of 0.20 molar. So we'll put 0.20 there. Again, water is not going to participate in this. We're going to ignore that. And we're going to start with 0 amount here. And finally, we're going to know, we know that's going to shift towards the products because there's 0 products. It's going to make product. So we're going to lose an X amount here. We're going to gain an X amount here. We're going to gain an X amount there. So our equilibrium amounts in terms of X is going to be 0.20 minus X. And this is going to be X, and this is going to be X. So now we can set up our Ka expression. So Ka is going to be equal to the concentration of products over the concentration of reactants. So here we're going to have the concentration of H3O plus, the hydronium ion, multiplied by the concentration of A minus, the conjugate base, or the anion of the weak acid. And then we got the divided by the concentration of the weak acid reactant. So HA on the bottom. So this is going to be equal to, as we said, oh, and by the way, this is equal to this over here. So Ka is equal to 1.002 times 10 to the negative 4. Okay, now notice here that this is 10 to the negative 4. This is the concentration 0.2. That's 2 times 10 to the negative 1. That's a difference by a factor of 1,000. So there's a good chance, that's a good indication that we can make the X is small approximation, or X is negligible, meaning that X here is so small that the change here, meaning that the change here is so slight that if I was to subtract X from 0.20, I would essentially still have 0.20 for my equilibrium concentration. So basically the equilibrium concentration is going to be the same as the starting concentration or initial concentration. So in that case, we can ignore X for this. So if we plug everything in, we'll see what we're talking about. So we'll have X times X, because both of these are X for the equilibrium concentration. And then we'll put in the concentration here for HA. So that's going to be 0.20 minus X. And so since this is so small, we're going to eliminate X from here. So we get X squared over 0.20, and that's going to be equal to 1.002 times 10 to the negative 4. And then you solve for X, right, by multiplying both sides by 0.2, and then take the square root. When you do that, you get X is equal to 4.477. 4.477 times 10 to the negative 3. And then if you calculate this, now this is going to be equal to X, and X, as we said, is equal to the hydronium ion concentration. So this is equal to the H plus concentration, the same as the hydronium. Hydronium ion is the H plus ion. So now we have the H plus ion, and again, we're supposed to find the pH. So we know that pH, again, is equal to negative log of the H plus concentration. So this is the H plus concentration. So that's going to be equal to negative log times 4.477 times 10 to the negative 3. And that's going to be equal to 2.348. 2.348, round that to 2 decimal places, so 2.35. So there's your pH of the chlorobenzoic acid solution, the 0.20 molar chlorobenzoic acid solution. I hope this is helpful. If you enjoyed this video and if this video helped you in any way, then please by all means like the video, share the video, hit that like button. Also, subscribe to my channel, help me out. Also, click the notification bell, and when you do that, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.